All right, so physics is full of these just deep, deep mysteries, right? But what if I told you that one of the biggest ones, I'm talking about the precise mass of the electron, might have a shockingly simple answer? Well, that's the question at the heart of this fascinating new idea called relator theory. And today, you guessed it, we're going to dive right in. So let's just start with the big question right up front. Why does an electron have the mass that it does? I mean, why that specific number? Think about it. The electron, it's a fundamental building block of literally everything, our entire reality. If you change its mass just a tiny, tiny bit, poof, atoms, chemistry, life as we know it, it all just falls apart. So yeah, the value is absolutely crucial. But the reason for that value, well, that's still one of the biggest question marks in all of physics. You see, this is where we hit a pretty big wall in our understanding. Our best theory of particle physics, you've probably heard of it, the Standard Model, it's amazingly successful. I mean, it's a beast. But it can't predict the electron's mass. It just can't. Instead, physicists have to go out, measure it with incredible precision, and then they just plug that number into the equations. It's like a known variable they have to feed in. It's an input, a given. It's not an answer that actually comes out of the theory itself. And that's a big deal. So the big question is, how do we get past that? How do we go from just measuring something to actually predicting it? Well, this new idea offers a potential clue. It's called the Relator Lock. So what exactly is this Relator Lock? Okay, this is the absolute heart of the whole idea. The theory says, hey, let's imagine an electron isn't just a tiny dimensionless dot. Instead, it has some kind of effective size, or radius, which we'll call r. And it also has this constant internal motion. You can think of it like a perpetual hum, with a frequency we'll call omega. Now here's the core rule, the postulate. These two things, its size and its hum, they aren't independent. They're locked together, and their product, r times omega, always equals one of the most fundamental constants in the universe, the speed of light. Yep, it all boils down to this beautifully simple equation, r omega equals c. A particle's effective size times its internal rotational frequency equals the cosmic speed limit. That's it. That's the whole rule. And what this one simple equation is proposing is a direct link between the geometry of an electron and, well, the very fabric of space-time itself. Pretty profound, right? Okay, so to really get a feel for this, let's use a classic analogy you've probably seen 1,000 times. The spinning ice skater, right? When her arms are stretched way out, she's got a big radius and she spins pretty slowly. But then, when she pulls her arms in, her radius shrinks, and what happens? Whoosh! She speeds way, way up to conserve angular momentum. We all know this. But now imagine there's a new unbreakable law of physics just for her. The rule is the speed of her hands at the very edge of her spin must always equal the speed of light. Now that changes everything. It creates this rigid connection, a lock, between her size and her spin rate. If she tries to pull her arms in even a little, her spin has to increase by a very precise amount to keep her hands moving at that constant speed. That is the core idea of the relator lock. Okay, a simple rule is great, a cool analogy is nice, but does it actually do anything useful? Well, this is where things get really exciting. The authors of this theory took this single postulate, and this is key, with no adjustable numbers, no fudge factors, and they used it to calculate the electron's mass from scratch. And the result? It's pretty remarkable. So, here are the numbers. Take a look. That top row, that's our gold standard. That's the value for the electron's mass that we've measured in countless experiments. Now look at the number right below it. That's the one calculated purely from relator theory. I mean, just looking at them, they're almost identical. But that last column, that's what tells us just how incredibly close they really are. The difference is just negative 2.45 parts per million. Let that sink in. A part per million is 1 in a million. This is just over 2 of those. That is astonishingly accurate. I mean, to get a number this close to the real-world value from a brand new theoretical framework, especially one with no knobs to tune or anything, that's a huge deal. It's a very, very strong sign that this idea is worth taking seriously. All right, so case closed, right? We've solved it. Well, not so fast. With a result this precise, it's really tempting to just declare victory. But that's not how science works. We have to be super clear about what has actually been shown versus what's still just a proposal. So let's break that down. Okay, so here's the split. What's been demonstrated is a huge mathematical success, no question. They've built this new, self-consistent framework based on that one simple relator lock rule, and it spits out a number for the electron's mass that is stunningly close to reality. That's a fact. But what is still just a proposal or a conjecture is whether this framework is actually a correct description of how nature really truly works. I like to think of it this way. They've drawn a beautiful, elegant map that leads directly to the right treasure chest. But we still need to prove that it's a map of the real world and not just a very, very clever coincidence. And proving that, well, that means asking a whole bunch of new questions. Look, this theory is brand new, and there's a lot it doesn't explain yet. And to their credit, the authors are the first to point this out. For example, where does electric charge even come from in this model? Okay, great, you got the electron's mass, but can the same framework predict the masses of other particles, like its heavier cousins, the muon and the tau? And is there a deeper connection to gravity here? These are the next big hurdles that the theory absolutely has to clear if it's going to stick around. And that really leaves us with this one final tantalizing thought. For centuries, physicists have been on this quest for simplicity, for elegance in the fundamental laws of nature. And what this theory proposes is that the mass of one of the most important building blocks of our entire universe is dictated by a single, incredibly simple relationship, R omega equals C. It's a bold idea, it's a beautiful idea. And while, yeah, there is so much more work to be done, it really does make you wonder, doesn't it? Could the universe, could it really be built on such a simple rule?